Betelgeuse, a red supergiant doomed to a short life and a violent death, a death which is, in cosmic terms, imminent. It's one of the largest stars we can see, and the seventh largest in the whole Milky Way at nearly 900 times the size of the Sun. It's so enormous that if it was at the center of our solar system, it would completely engulf Mars, and its edge would be close to Jupiter's orbit. It's big. Only 13% of the energy emitted from the red supergiant is visible light. If we could see the remaining 87%, it would easily outshine every star in the sky except for the Sun, and it's already, on average, it fluctuates, one of the 10 brightest stars. If the Sun and Betelgeuse were the same distance from us, we'd see Betelgeuse shine 100,000 times more brightly. But lately, the red giant star has dimmed dramatically, leading some scientists believe that it may soon turn to a supernova. This explosion promises to be spectacular. The star will detonate with the force of 10 million suns, burning bright enough to be visible across half the known universe. From Earth, it will appear to glow more intensely than the full moon, luminous enough to cast shadows at night and to shine through the midday sunlight. Join us as we uncover the brightest supernova observed from Earth in more than 400 years and its impact on our planet as well as the universe. Today, Betelgeuse appears as a red star shining brightly in the corner of Orion. However, ancient Chinese astronomers described the star as yellow, contrasting it with the red of Antares. The Romans spoke of it likewise, comparing its hue to that of Saturn. Sometime around the 1st century, its tone started to shift. Ptolemy, writing in the mid-2nd century, called it a tawny orange. By the Middle Ages, when observations became more systematic, its color had become as firmly red as Antares. This shift hints at a possible transformation in the nature of Betelgeuse. Many supergiant stars start out yellow, but gradually fade to red as they cool. This transition can happen quickly, taking place over a few thousand years at most. If this is what happened to Betelgeuse, then it suggests it is a young supergiant star, and, in all likelihood, one that has a while yet to live. Still, Betelgeuse has not only changed in color, but also in brightness. Though it has almost always appeared as one of the brightest stars in the sky, its ranking among those stars has risen and fallen over time. Betelgeuse, it seems, fades and brightens in the sky, waxing and waning in strength over the years. Over the past 2 centuries, modern telescopes have uncovered a scientific reason for this. Betelgeuse is a pulsating star, one that shrinks and expands roughly once every 400 days. That, in turn, creates a variation in its brightness, albeit one that appears to be unsteadily laid over various longer-term cycles. However, recently, that cycle seems to have broken down. Early in 2019, Betelgeuse began to dim, just as researchers had expected. But instead of later beginning to brighten again, it kept getting darker and darker. By the end of the year, the star was fainter than it had been in at least a century, and so had lost its place among the 20 brightest stars. This behavior baffled scientists and led to speculation that a supernova was imminent. Could it be, some wondered, the sign of an unexpected disturbance rippling through the star, an indicator of dramatic changes to come? Within weeks, though, the star was brightening again, and by August 2020, it had apparently returned to normal. No supernova followed, at least not yet, and the star has not dimmed so dramatically again. Whatever had happened to the star, it seemed to be a temporary hiccup, a blip that had soon passed. In the end, it was a weather satellite that provided the answers. By chance, the Japanese Himawari 8 satellite had caught images of Betelgeuse stretching over a period of several months. For astronomers, this was a stroke of good luck, offering them a chance to see exactly how the star had changed in the weeks leading up to the great dimming of 2019. Betelgeuse, they found, had blown out a vast belch of stellar material. As this moved away from the star and cooled, it formed a dust cloud, blocking much of the light coming from the star. From Earth, we saw this as an unexpected darkening of the star. Although the dust cloud has since dissipated and Betelgeuse has regained its usual brightness, the star has not been quite its old self since. Its 400-day brightness oscillation period has halved to 200 days, and, on top of that, in the spring of 2023, the star began to brighten beyond its usual peak luminosity. Betelgeuse's antics prompted speculations that the star might soon explode in a supernova. Supernova explosions are the swan song of very massive stars. After they consume all of the helium in their cores, red giants begin to burn carbon and oxygen into neon and magnesium, then burn those into silicon. Eventually, the star's cores fill with iron, and that's when the fireworks begin. Scientists think Betelgeuse will happen sometime in the next 100,000 years. Yep, it's a long time in human terms, but in cosmic terms, that's a blink of an eye. The red supergiant's life will be short and frenzied. Our sun, currently approaching the midway point of its life, can expect to live for 10 billion years, but Betelgeuse will only live for roughly 1,000th of that time. The star is scheduled to die at around 10 million years old. Whilst Betelgeuse has shone throughout the existence of humans, other apes evolved long before Betelgeuse burst into life. Compared to other stars, that's an astoundingly short life for a star. And this is because of its mass. It has around 20 times the mass of our sun. And that means it has burned through its fuel very, very quickly indeed. And one day, just like every other star, Betelgeuse will run out of fuel. It's the fate of every star. But how massive a star is defines its end. The nuclear fusion at the heart of our sun, for example, is fusing hydrogen into helium. Once all the helium is gone, it'll transform into a red giant and get hot enough to fuse helium into carbon, which, in turn, will combine with helium to form oxygen. Eventually, gravity will lose, and the sun's outer layers will dissipate away, leaving a dead white dwarf. This isn't the fate that awaits Betelgeuse. Betelgeuse is so massive and hot in the center that it is able to fuse much heavier elements like calcium and silicon. It's a red supergiant, and it is destined for a far more vicious death. But what would happen if Betelgeuse burst right now? Well, in the final minutes of its life, the core will be so hot that elements like iron, nickel, and cobalt will be fused. But these elements won't fuse into anything heavier, so when all of the silicon is consumed, there will be nothing more to fuel the star. Gravity pulls inwards, but nuclear fusion is no longer pushing outwards, and so the star begins to implode at an alarmingly rapid pace. Unable to withstand the pressure, runaway fusion begins, leading to a supernova explosion. The explosion disintegrates the outer layers of the star's matter, which will be scattered into the darkness beyond, ready to give life to new stars. But we can't know exactly what will happen next. Betelgeuse could become an ultra-dense neutron star, or it could collapse and become a black hole. It rather depends upon how much matter remains in the center of the star after the supernova explosion. If we are fortunate enough to see Betelgeuse go supernova in our lifetimes, we'll see something extraordinary. In the final throes of its short life, from Earth, Betelgeuse will shine nearly as brightly as the moon for over 3 months, as radioactive cobalt and gases shine. Betelgeuse will shine billions of times brighter than the sun. Fortunate, then, that such a long distance protects us from the explosion. The cataclysmic death of this enormous star will even be visible during the day from Earth. Over the course of the next couple of millennia, the majesty of this tempestuous star, which has shone above every generation of humans ever to walk the Earth, will fade from our view forever. Of course, such things have happened before. Roughly twice a century, astronomers calculate, a star explodes somewhere in our galaxy. Yet most do so far away, and so their light is obscured by clouds of dust and gas, rendering them invisible to the human eye. Historical records speak of just 4 visible supernovae in the past millennium, the last of which erupted in 1604. So, just a few people are lucky enough to see one. Even fewer will see one as bright as that promised by Betelgeuse. of which only one in recorded history, that of the year 1006, comes close. Records speak of a new star appearing at the end of March that year, burning strongly enough to be seen during the day and at night, casting shadows on the ground. For months it shone, appearing brighter and larger than even Venus. But in those days, observers knew little of what caused such guest stars to suddenly appear in the sky. In China, astrologers interpreted it as a sign of prosperity, reporting it to the emperor as an auspicious omen. Others saw it as a portent of famine and plague, a warning of a coming disaster. 9 centuries later, with the advantages offered by modern telescopes, a pair of American astronomers found the resting place of that long-ago supernova. It lies some 7,000 light-years from Earth, marked by an expanding shell of glowing gas. At the heart of it should be a remnant, either a black hole or a neutron star, formed in the heat of the supernova. Yet so far, at least, nothing has been spotted. Betelgeuse, at a distance of roughly 700 light-years, is 10 times closer than the 1006 supernova. It lies close enough, indeed, that some commentators worry its demise may have dramatic effects on our planet. Shockwaves from such a nearby supernova, they fret, could slam into the solar system. Radiation from it could strip the ozone layer and poison the atmosphere. This nightmare scenario is unlikely. Betelgeuse is close, but not that close. A supernova would need to detonate within 100 light-years or so to be a real danger. And at present, no known star presents such a risk. Similar events have probably happened in the past, but on a timescale of once every 100 million years or so. Then, the supernova of Betelgeuse promises to be a spectacular event, one that humanity can enjoy without fear of famine or plague. When it erupts, it will shine far more brightly than the event of 1006, more brightly, in all probability, than any other supernova since the dawn of civilization. With a promise of such a spectacle, it is no surprise that sky watchers wish for Betelgeuse to die. But as told, we will probably see it happen sometime in the next 100,000 years, a blink in cosmic terms, but unfortunately an extremely long time for mortal humankind. On the other hand, it is worth noting that when we study stars, we are looking at the past. Because Betelgeuse is 640 light-years away from us, it's interesting to think that it could have gone supernova any time since the 14th century and we still wouldn't know about it. Either way, when humans finally see Betelgeuse's last moments, it will certainly be a magnificent celestial spectacle like no other. When astronomers dig deep into supernova explosion, they found that these supernovas are whipping up a storm, contributing to cosmic life and death. The international team has just spotted that a hitherto unknown source of the cosmic dust basically acting as building blocks for stars that can be created by a type of cosmic explosion that occurs when a dead white dwarf star strips material from a stellar companion, then interacts with gas from its immediate surroundings. These events are called Type 1 supernovas and are often referred to as standard candles by astronomers because their uniform light output can be used to measure cosmic distances. As Lifan Wang, a team member and Texas A&M University astronomer, said in a statement, "The formation of cosmic dust is of critical importance in astronomy. It is related to literally all phenomena of the cosmos. Understanding the process by which it forms has been one of the key objectives of many modern-day astronomical missions." This isn't the first time supernovas have been associated with the creation of cosmic dust, but previous observations have revolved around core collapse supernovas. These happen when a massive star runs out of the fuel supply required for its intrinsic nuclear fusion processes. This forces the star's core to collapse, birthing a black hole or a neutron star, while the star's outer layers are blasted away in a supernova explosion. However, core collapse supernovas aren't seen to occur in elliptical galaxies that resemble giant swarms of stars. rather than organized spirals like the Milky Way. Thus, astronomers have struggled to explain where the dust in elliptical galaxies specifically originates. Wang and colleagues have now supplied an answer. This dust could be coming from vampire white dwarfs, feeding on a cosmic companion before blowing their tops in a thermonuclear explosion. All life forms in the universe are cosmic dust forged in processes related to stellar evolution, Wang said. Our paper presents clear evidence of the condensation of a massive amount of dust particles after the explosion of a white dwarf star. White dwarfs are dense stellar corpses born when smaller stars run out of their fuel needed for nuclear fusion, and their cores collapse. However, those petite stellar bodies lack the mass necessary to drive a complete collapse, which would birth a black hole or neutron star. Instead, they form white dwarfs. Our own sun will undergo this process when it exhausts the hydrogen supply at its core in around 5 billion years. But while our sun will have a lonely death as a cooling white dwarf, some white dwarfs exist in binary systems with companion stars that they can use to spring back to life. If these stars are close enough to one another, the white dwarf can steal material from the outer layers of its stellar companion. This stolen matter first forms a disk around the white dwarf, and from there inches toward the star's surface. This accreted matter eventually piles up, increasing the mass of the white dwarf beyond what is called the Chandrasekhar limit, equal to 1.4 times the mass of the Sun and representative of the mass limit at which a star is capable of going supernova. This all ultimately gives rise to a thermonuclear explosion called a Type 1a supernova. To determine if Type 1a supernovas could account for cosmic dust, Wang and colleagues observed a supernova named SNN 2018 EVT for over 3 years, using a combination of space-based instruments such as NASA's Spitzer Space Telescope and the NEOWISE mission, and several ground-based observatories. They found that the supernova collided with material that had been cast off from stars in the binary system, and saw the white dwarf feeding on its companion prior to the former's thermonuclear fate. This collision, the team observed, sends shock waves through that cast-off gas, with dust forming in the gas itself as it cools after the shock waves have passed. The telltale signature of dust creation in this supernova had to do with its dimming in optical light and brightening in infrared light. From this, the team estimated the collision was responsible for creating a massive amount of dust equivalent to around 1% of the mass of the Sun. And, as the gas cools further, the team believes dust production will increase by as much as 10 times. As Lingji Wang, team member and a scientist at the Chinese Academy of Sciences South America Center for Astronomy in Chile, said, "The origins of cosmic dust have long been a mystery. This research marks the first detection of a significant and rapid dust formation process in the thermonuclear supernova interacting with circumstellar gas. From this research, it seems Type 1a supernovas aren't quite as efficient at producing gas as their core collapse counterparts. This deficiency may be offset by the fact that there may be enough Type 1a supernovas interacting with their surroundings to be a significant, or even dominant, source of dust in elliptical galaxies. This work offers insights into the contribution of thermonuclear supernovae to cosmic dust, and more such events may be expected to be found in the era of the James Webb Space Telescope. The Webb telescope sees infrared light, which is perfect for the detection of dust. The team's revelations show that white dwarfs can also play an important role in the ongoing cycle of star formation and destruction, as well as in the processes that give rise to planets, and sometimes life as we know it. As Las Cumbres Observatory scientist Andy Howell said, "The creation of dust is just gas getting cold enough to condense. One day, that dust will condense into planetesimals and ultimately, planets. This is creation starting anew in the wake of stellar death. It is exciting to understand another link in the circle of life and death in the universe." In addition, a new observations made with the James Webb Space Telescope just revealed that 2 dwarf planets within our solar system, named Eris and Makemake, might exhibit enough geothermal activity to maintain oceans of liquid water within. Found deep in the Kuiper Belt, Eris is the icy world that, when it was discovered in January 2005, threw Pluto's status in the solar system into crisis. Just 44 kilometers smaller than Pluto, but 25% more massive thanks to a greater concentration of rock in its core, Eris became the prototype dwarf planet. Pluto was inevitably forced to follow suit. Makemake, pronounced Ma-kai, was spotted 2 months after Eris, and at 1430 kilometers across is about 1,000 kilometers smaller than Eris and Pluto. Their great distance from the Sun, Eris is currently 14.4 billion kilometers away, and Makemake is 7.7 billion kilometers away, means little is known about these faraway dwarf planets. However, recent observations with the James Webb Space Telescope have shed new light on the worlds, finding a surprising origin for the frozen methane ice on their surface. Methane is what's known as a hydrocarbon, in that it is formed from a mixture of hydrogen and carbon atoms. Those atoms can come in different flavors, or isotopes, containing the same number of protons but different numbers of neutrons. If the methane on these dwarf planets' surfaces had been accreted from the primordial planet-forming disk that existed around the young Sun 4.5 billion years ago, they would contain a certain isotopic ratio between two isotopes of hydrogen, regular hydrogen, with 1 proton and 0 neutrons, and deuterium, with 1 proton and 1 neutron. However, the hydrogen isotope ratio measured by James Webb is different to the ratio that would be expected if the methane were primordial, as we see on most comets. As Christopher Glein, a planetary geochemist from Texas Southwest Research Institute, said, "The deuterium-hydrogen ratio points to geochemical origins for methane produced in the deep interior. Our data suggest elevated temperatures in the rocky cores of these worlds, so that methane can be cooked up. Molecular nitrogen could be produced as well, and we see it on Eris." In other words, hydrothermal reactions, or metamorphic activity, which refers to heat and pressure acting on rocks, must have produced the methane deep inside Eris and Makemake. Then, that methane must have made its way to the surface via outgassing or even volcanism. For methane to form in this manner, a temperature in excess of 150 degrees Celsius is required. These temperatures could only come from radioactive isotopes present within the rocky cores of each dwarf planet, giving off heat as the isotopes decay. Hot cores could also point to potential sources of liquid water beneath their icy surface, said Glein, raising the possibility that Eris and Makemake could contain possibly habitable oceans. The outgassing of methane onto the surface may have been happening until recently, according to another isotope ratio between carbon-12, which has 6 protons and 6 neutrons, and carbon-13, which has 6 protons and 7 neutrons. If Eris and Makemake hosted, or perhaps could still host warm, or even hot, geochemistry in their rocky cores, cryovolcanic processes could then deliver methane to the surfaces of these planets, perhaps in geologically recent times, said Will Grundy of Lowell Observatory, who led the initial James Webb observations. We found a carbon isotope ratio that suggests relatively recent resurfacing. Intriguingly, the models developed to describe the formation and outgassing of methane on Eris and Makemake could also apply to Saturn's moon Titan. Research published earlier this month indicated that methane and other carbon-based molecules important for life might not be able to reach Titan's subsurface ocean after hanging out on the surface for a bit, where hydrocarbons are plentiful. This called into question the presumed possible habitability of Titan's ocean. However, if methane and other gases can form geothermally within the rocky core of Titan, as they do on Eris and Makemake, then Titan's ocean could get its supply of carbon chemistry from within the planet rather than from its surface. The results of the methane observations on Eris and Makemake are described in a paper published in the April 2024 issue of the journal Icarus. That's all the information that we have for you today. Don't forget to give us a thumbs up if you enjoyed today's episode, subscribe if you haven't already, and hit the bell so you never miss out on future episodes. And be sure to also tell us what you think about today's content. Everyone's support motivates us to continue delivering quality content and to always improve. As always, thanks for watching, and we will see you next time.